Hello there, welcome in this new video of the State Space Control channel. Today I will be sharing you the very nice results of 8 teams of control engineering students at ICA. These projects were carried out during the Advanced Control on Embedded Systems activity, which itself is part of the Advanced Control 2 teaching unit. The work was supervised by my colleague Sebastian van Koenberg and myself, Franky de Bruyne. The format of the laboratory has remained unchanged in comparison with previous years. We still work with 2 types of robots, the EduMiP, which is Linux based, and the Balboa, which is Arduino based. Each team is free to choose its own project topic. The only requirement is that the solution must implement a state space observer and a state space controller. We also apply a customer-supplier approach. In this setup, the supervisors act as the customers, expecting a solution that goes beyond the current state of the art, that is, the work that has been done previously. It's essential that both the customer and the supplier agree on the expected deliverables. This year we had 8 projects in total, 5 working with the Balboa platform and 3 using the EduMiP. Without giving too much away, here's a preview of what you can expect. I'll start first with the Balboa teams. You have here a path-following transporter robot that stops precisely at color-coded locations, a robot that navigates back to its base while detecting and avoiding obstacles, a clever robot capable of escaping any maze regardless of its structure, a chess-playing robot that moves to specific board locations controlled via an Android app, and then a voice-controlled robot using fully offline onboard speech processing. No internet is required. Next we have the EduMiP teams. First we have Kevin, clearly a soccer-playing robot named in honor of the greatest football player ever, which is incidentally named after me. Next we have a color path following robot that adjusts its behavior dynamically based on the color it detects, and a hand-free robot controlled through gesture and movement detection, a great example of intuitive touchless interaction. Next, I will take you through each project in a bit more detail. I will be using the team's own slide presentations as a starting point. I have trimmed things down to keep it short and sweet. The focus will be on presenting the core of each solution along with the all-important factory acceptance test, or FAT. Yes, even robots need to pass their exams. Unfortunately, I had to leave out some of the cool music and video clips. It turns out that not everything on the internet is free, so stay tuned. These balancing robots have some impressive tricks up their sleeves. Remember that each robot has to do its task while keeping on balancing, as the process is open loop unstable. Mohamed Assoufi, Soufiane Ali and Alain Mbali make up Balboa Team 1. Their objective is path following and transportation. They do this using the inbuilt 5-channel sensor array that is mounted below the robot. They've added a color sensor and a transportation platform. On the platform, what you have is an ER sensor for object detection. In this way, they can transport an object from one color spot to another. As I said, the actual line tracking is done by the 5 ER sensors that are mounted below the robot. They have written 2 functions, a function line detection to detect the line, and then a function line tracking that does the precise tracking of the black line. As you can see, this is working fine on an actual track. Here on the right, you see some I/O testing. Right, you have a black stripe underneath the leftmost ER sensor, and this is clearly detected. And if you put a line across all sensors, this is also clearly visible. The team used an RGB color sensor, and this is the way it is connected to the Balboa. They also performed I/O tests for red, yellow and blue detection, right? And the idea is that once a color is detected, the robot performs a predefined action, and this is working fine, as you can see here at the bottom, right? The team had a huge delay in the project due to a damaged sensor. And finally, they have added an ER sensor to test the presence of a transported object. Once an object is detected, it triggers a specific robot action, for instance, leaving a location. We can have a look now at the factory acceptance test. This is the test that tests the overall team problem. As you will see in the video, the robot struggles a little bit to follow the line and to detect the colors. There is some extra wobbling, and this has probably to do with the ER sensor integration. It could be that this ER sensor is connected to a pin that is conflicting with some other tasks, such as the line following. Although the datasheet suggests that there is no conflict, it could be that there is signal interference or that there are timing conflicts between the sensors and or the balancing algorithm. Since there was a late delivery of the new color sensor, there was no time to look at those problems. Majda Ati, Safed Jamawi, and Umayma Benaish make up Balboa Team 2. They have taken up the base station problem, in which the robot has to find back its bases, despite obstacles that it has to detect and avoid. Imagine a vacuum robot moving around the house. It cleans the floor while avoiding obstacles. If it detects an obstacle, it will navigate around it. Once the cleaning is done, it returns to its base charging station. Here's an important detail. The vacuum cleaner is open loop stable. In contrast, the mobile robot is not open loop stable. It requires feedback to retain stability, which makes the task much more complicated. This setup involves two main hardware components: a base station equipped with 4 ER emitters connected to an Arduino Mega board, a Balboa, right, featuring an ER receiver, right, and an ultrasonic distance measurement for obstacle avoidance. The ER receiver is of course to align with the base. Additionally, a TV style remote control is used to stop the robot when it approaches the base. If you're thinking of recreating the project during the holidays, here is the bill of materials. The 4 ER emitters in the Arduino Mega make up the base station, and the ER receiver and the ultrasonic sensor has to be mounted on the Balboa mobile robot. Additionally, you need a remote control. Here you have the schematics of the base station with the 4 emitters, ER emitters, and how they are connected to the Arduino Mega. There is also an ER sensor to see if the mobile robot is close to the base and then send a stop command, but in the end this sensor was not used and instead a remote control was used. This is the schematics of the connection of the ER sensor and the ultrasonic sensor to the Balboa mobile robot and to its board. This drawing shows that there is a very important balance to keep between the balancing algorithm and the measurement tasks. This balancing algorithm runs at a sampling period of 10 milliseconds and there should be no timing overruns. If the timing overrun is too large, since the process is open loop unstable, the robot will simply fall. This is why you have to work with interrupts so that this main task has no timing overruns. If you look at the schematics of the Balboa, you will see that there are 2 pins that support interrupts, pin 0 and pin 1. And since of course we first want to avoid an object and then turn to the base, you should give priority to the ultrasonic measurement by connecting it to pin 0. In the following video you can see the base station with this proximity ER sensor. As you can see, the run command is sent by the base, and when something approaches this proximity switch, a stop command is sent. The next video shows the very good reaction to an obstacle, And this happens without interfering with the main task of balancing the robot. This is the result of working with interrupts. And now it's time for the factory acceptance test. In this video that has been accelerated by a factor 3, you can clearly see that the robot is capable of finding its base while avoiding the obstacles. Mehdi Atigui, Antoine Chevalier, Abderrahman Lizati make up Balboa Team 3. They have taken up the maze robot problem. The goal of this project is for the robot to escape from a maze, but not just any maze. The challenge is to design an algorithm that works across a variety of labyrinths with a level of complexity higher than what we've seen in previous years. What sets this project apart is the team's clever solution for testing. They developed a modular system of interlocking maze boards. This allows them to quickly build different maze configurations in record time. It's a great way to test the robustness of their algorithm, and the best part is that these maze sections are reusable, making them a valuable tool for future student projects. For this project, they have used 3 ultrasonic distance sensors, 1 mounted at the front and 2 on the side. The ones mounted on the side are also used to readjust the position of the mobile robot when driving between 2 walls. In the adapt angle function, 2 successive distance measurements to the wall are used to give an indication of the heading. This heading is then corrected using the relative speed of the left and right wheels. In this first video, we see that the mobile robot is able to use its ultrasonic sensors to avoid obstacles, here the walls, in a confined space. And now it's time for the final factory acceptance test when confronted with a complex maze. As you will see, the robot is capable of escaping the maze. Further improvements can be made when it comes to robustness. Especially 90-degree turns are sometimes problematic as they are done in open loop. Interference with the main algorithm is also a topic, which has no easy solution as the Balboa has only 2 interruptible pins, whereas 3 sensors are used. It's also worth mentioning that the team came up with an algorithm to find an optimized return path that is cutting out unnecessary loops and getting straight to the exit. So it's not just getting out of the maze, it's getting out smart. So let's hope next year another team will take up the challenge and implement this future improvement. Julien Carpentier and Ronaldo Imelecana make up Balboa Team 4. They have taken up the chessboard robot problem. The objectives and functionalities are to navigate on a 4x4 chessboard, to receive movement commands via Bluetooth and an Android app, to detect black and white tiles using the ER sensors mounted below the Balboa robot. This is to locate the robot on the chessboard, and to perform straight and rotated movements. As a bonus, as you can see on the right, they have also included joystick motion. The robot will always start from square A1, that's where the red cross is. A movement is always done in straight lines, and a movement, in this case for instance D4, is split into 2 phases. A column instruction, go from A to D, and a row instruction, go from 1 to 4. And for instance, to go from row 1 to row 4, well, you need 4 black and white transitions, and that's why they are counted. This is the way to locate the robot on the chessboard. Recentering of the robot on the tile is done after each move, and after each instruction the robot performs a short rotation to reorient. So here are the components that make up the system. Of course, you need a Balboa robot, you need a prototyping board, you need an HC05 Bluetooth module that you can see over here, and here it is mounted on the robot, and you need the Well, QTR infrared sensor array. Remember that there are 5 infrared sensors. Of course, you need also an Android smartphone to enter the moves, and this interface has been constructed using the Android Bluetooth controller app. What you see over here is the connection scheme for the HC05 Bluetooth module, here to an Arduino Uno, but it's very similar when connecting to the Balboa. Note that the HC05 only accepts 3.3 volts on its RX or receive pin, and therefore a voltage divider is needed. So how does this work? The Balboa robot receives a command through its Bluetooth interface, then the path is calculated. The straight line movement is done by detecting black-white transitions, right? A 90-degree rotation is performed if necessary, and of course dynamic balancing is done during the movement. Stop and calibration is done on the target square to readjust the position of the robot on the tile. And let us now have a look at the very convincing factory acceptance test. Laetitia de Bock and Nathan Scriven make up Balboa Team 5. They have worked on the voice-controlled Balboa robot. The team problem is to use Vosk, an open-source speech recognition toolkit that runs entirely offline, and it is run on a Raspberry Pi that is attached to the Balboa. The commands are, for instance, go forward and then stop, go back and then stop, and turn and then stop. There is always the risk that when the robot is moving, the stop command is not recognized. The solution is to replace the commands go forward and go back by go forward and go back with a certain distance. The turn command is replaced by turn left or turn right with an angle of 90 degrees. To run the real-time speech recognition using pre-trained models that can recognize speech in French, well, you need additional computational power. You don't have enough with the Balboa Arduino type processor, so a Raspberry Pi 4 Model B is used. Of course, you need a microphone, you need power, so this is why there's also a DC-DC converter to convert the battery voltage, which is just below 9 volts, to the needed 5 volts of the Raspberry Pi. And of course you need also an interface USB to micro USB for the serial communication between the Raspberry Pi and the Balboa board. To ensure stable mounting of the Raspberry Pi, a 3D printed support part was designed, and the neat thing is that this part can be reused for future projects. On the right, the voice command through the microphone, for instance go forward 10 cm, is translated in a 5-digit formatted message. This format will be explained next. This message is then transmitted to the Balboa via serial communication. On the left you can see that this command is processed and results in set point updates to the different state space controllers. So here's a list of the protocol of commands from the Raspberry Pi to the Arduino. The first digit has to do with the command type, go forward, backward, turn or fall. The next 3 digits have a meaning of distance or angle, and the last digit has to do with the unit, either meter or centimeter. This team clearly embraced the classical principle of divide and conquer. One team member focused on the interpretation of the voice commands and their conversion into this 5-digit format. This was work developed on the Raspberry Pi. At the same time, the other team member was working on the Balboa Arduino, handling the processing of those 5-digit codes through the terminal and translating them in robot movements. The advantage, well, they could work in parallel, each on their own platform, without stepping on each other's toes and without losing time. And once both parts were up and running, all that remained was to get the two processors talking to each other, and the system was ready to go.
Recule de 50 cm. Reculer de 50 cm. Tourne à gauche. Tourne à droite. Tourne à droite. Tourne à droite. Recule de 50 cm. Avance de 50 cm. Recule de 20 cm. Reculer de 20 cm. Reculer de 20 cm. Tombe. Tomber. Tomber.
As you might have noticed, the robot does not always respond to voice commands, but you have to remember that the voice recognition is offline. Vosk uses pre-trained speech recognition models, and these are not specifically adapted to Laetitia's or Nathan's voice. Vosk was chosen because it is lightweight and it runs efficiently on a Raspberry Pi. And also you have to remember that the microphone is a simple basic USB model. So despite these limitations, the team has achieved impressive results within the available resources. Charles Jamard, Jonathan Skepens and Maxime de Martelard make up Team EduMiP 1. They have designed Kevin, the best soccer robot player ever. Well, I guess the objective is quite clear. Kevin has to locate the ball, align on the ball, go forward and kick the ball in the goal. This team decided to take on an entirely new problem, not one in the proposed list of team problems. They equipped the EduMiP with a Pixie 2 camera mounted using a custom 3D printed support. They also designed a mechanism to push or kick the ball, and yes, a robot player needs a ball, so they went for a ping pong ball. A creative and autonomous approach from concept to hardware. These are the challenges that have been solved during the project. First, implementing the state space controller, that is the digital implementation and the optimization of the pole locations. This is not covered in this video as it focuses on the team problems. Second, the ball detection. This involves teaching the camera to recognize the ball, a major problem in itself if you want to do this in a robust fashion. The information has then to be sent to the EduMiP using UART serial communication. You can see a video below showing the teaching process. Third, the ball position. The important parameter is the angle of the ball relative to the front of the robot. To isolate the image processing from the control balancing control loop, a thread is used. So the image processing, which involves filtering and computation of the angle, runs in a separate vision thread for parallel execution. The fourth challenge is heading control. The ball's angle relative to the EduMIP's forward axis is used to control the robot and help it align its heading towards the ball. And here you have the wiring diagram to connect the Pixie 2 camera to the BeagleBone Blue. As I said, it's UART communication. And as I said also, the camera data processing code runs in a separate vision thread. In this video, you get an idea of what Kevin sees with the onboard camera. Remember that the important parameter is the angle of the ball relative to the front of the EduMiP, not the distance. In this video, you can have a look at the heading control, so you can see how the onboard camera is used to align the robot on the ball. And finally, the factory acceptance test. As you can see, Kevin, the soccer player, successfully detects the ball, aligns, scores a wonderful goal. The final kick in an all-star performance. Jibril El Jaid, Eman Mejni and Habib Rifiaxnai make up Team EduMiP 2, and they've taken up the color-based path following problem. The objective is to follow a black line on the ground while balancing and to react to specific colors along the path. Here is the hardware that they used. Of course, they used the BeagleBone Blue and the EduMiP kit. Then they used a Arduino board with 3 ER sensors, right? Notice that there are only 3 ER sensors, whereas below the Balboa robot you have 5. So this makes the tracking problem a bit more complicated. They used also this RGB color sensor that was used also by Balboa Team 1. And with this new type of sensor, this year the color measurements have become more reliable. They've also adapted an existing mount to connect this ER sensor board to the robot and keep it parallel, and they've used counterweights to make it really parallel to the ground. In the end of the project, they suffered also a major setback because one of the axes connecting the mount to the wheels broke down, but they managed to print it again in time thanks to the ECAM Fab Lab. A big thanks to them for the support. The color sensor processing was handled in a separate thread in order not to interfere with the main balancing task. The detection of blue means that the robot will stop for 10 seconds, and the detection of red means that the robot will make a 5-second reverse. In this first video, Team EduMiP 2 showed that the line following is really robust. Notice also the U-turns at the end of a line. And now it's time for the final factory acceptance test. Remember that blue means a 10-second pause and that green means a 5-second reverse. This reverse will only be done once. Team EduMiP 2 have very good ideas for possible improvements for next year's projects, so I hope these ideas will get picked up. One idea would be to replace the IR sensors with a camera, and this camera would be able to detect T-junctions and colors. Another idea would be to add a web interface or a mobile app to monitor the sensors in real time and to send commands to the robot. Moulain Slimani Outi and Ibrahim Aourak make up Team EduMiP 3, and they have designed a hands-free robot. Well, this team have come up with their entirely new problem. They have submitted their specifications to the customer, Sébastien and myself, and we have accepted the problem. The objective is to control the EduMiP robot using hand gestures via a sensor, the APDS 9060 sensor. It's a versatile digital sensor that provides multiple sensing capabilities in a single module. It supports, as I said, gesture detection, but also proximity sensing, ambient light sensing, and RGB color sensing. So it's probably a sensor that we'll see in future projects. Well, here are the key requirements. It's necessary to detect 4 gestures, up, down, left and right. Each gesture has a specific robot movement associated to it. They use I2C communication to communicate between the sensor and the BeagleBone Blue, and of course responsiveness and integration on the BeagleBone Blue is a welcome feature. So here's how the sensor is connected to the BeagleBone Blue. Remember that integrated circuit I2C communication is used. SDA carries the data and SCL provides the timing for the synchronization. The big bone blue acts as the master and the sensor as a slave. On the screen you can see the I/O test of the sensor. Up, down and left, right commands are clearly picked up. Note that there is a detection thread for the interpretation of the gestures. This detection runs in parallel with the main program without blocking other tasks. Atomic or shared variables ensure synchronization between threads. Multiple threads can access these variables without conflicts. One such variable is the current gesture. In order to ensure a smooth and timely gesture detection, a number of actions had to be taken, and it was vital to dig in the parameter description of the sensor. For instance, it is important to set the polling rate of the sensor correctly in order for the sensor not to be scanned too often. Another key point is to filter out only valid gestures, so that only explicit known gestures such as up, down, left, right are processed. And finally, it's also useful to set the gesture to none at the end of each loop. All those actions have ensured a smooth interaction with the robot. And now it's time for the FAT test of the hands-free robot. As you can see, the gesture control is reliable, fast and convincing. This is the result of the thread implementation and the careful analysis of all the sensor and software parameters by Team EduMiP Team. The team encountered a few challenges. They had, for instance, to adapt and extend an existing sensor library. They had to do this in C. They had to learn to work with threads in C. There were very few resources available for this sensor in C. Most of the programming in projects is done in Python. And at the end of the project, they had a battery issue. But all those challenges were overcome and led to the very nice results that you have seen just before. A big thank you to all 8 teams for their hard work and motivation. The results are truly impressive. Special thanks also to my colleague Sébastien Van Kouwenberg for all the great collaboration work. I hope to be back next year with a brand new video. Ciao.